Question for you, Sean? All right. So, continue kind of with some of these examples. Let me give you a following definition / example. Suppose I have a sequence of groups. Groups and homomorphisms. Let's say, how am I indexing this? So it's just this is just sort of a big composition, if you will, of groups and morphisms. So complex. Yeah. The image of that thing contained in by the way, what does that mean? If the image of this is contained in the kernel of this, what happens when you compose these two in a row? Well, right, you get the zero homomorphism, right? This composition just takes G into the identity here. This seems like something I made up just to give you a definition because I've got nothing better to do with my life. However, this situation actually comes up quite often. And in fact, we can specialize this a little bit. We say this sequence is exact. Yeah. Image of that thing is equal to the kernel. And if you've ever heard of homological stuff, homological algebra, this comes up in topology and everything else. Basically, what they're doing is they are measuring the difference between a complex and an exact sequence, right? So they're measuring how much a complex just means that this containment. When you measure homology groups, you're sort of measuring how much this equality is missed by this in a certain sense. And it actually tells you things about topological spaces and all kinds of things, actually. So that's kind of for culture, if you will. Here's a proposition. I'm going to do some things about subgroups, intersections, and proposition 2.3.11. Let G be group and H some index family of subgroups. So this is G, and this is just a random collection of subgroups. Might be very large, might be indexed over an uncountable set, or might be indexed over a small set, finite set. Then G, then the intersection. This is a very important fact to notice that the intersection of a collection of subgroups is still a subgroup. Now, just so I can show off the subgroup criteria, let me sketch a proof of this real quick. So what I want to do is show that the intersection of all these subgroups is again a subgroup. So let me point out this is not the empty set, first of all, because since these are all subgroups, they all contain the identity of G, right? So certainly the identity is the intersection. Now that I've sort of cleared that hurdle, I now know I can use the subgroup criteria because that applies to a non-empty set. So suppose Y are an intersection. Really, this almost feels like kind of a beginning kind of proofs argument because it's really basically writing down what an intersection is. So for all I in that set, we have X, Y is an intersection. Therefore, for all I in the index set, X, Y inverse, right? Because each of these little animals is a subgroup, right? Therefore, X, Y inverse is an intersection. And so by the subgroup criteria, intersection. Okay. Now, I introduced this little theorem right here. Any questions? Now, there's a method to my madness. Why put this proposition right now? This allows me to do kind of the following sort of mathematical fancy thing. So definition. The group. So I'm assuming that there's something sort of parent group that contains this and X and G. We find the group generated by X. Well, subgroup G. X okay, so once I tell you what the answer is here, so to speak, I'm going to also give you sort of a working mathematician's way of thinking about this, sort of more practical way. But here's the fancy math way to do it. How do I define the subgroup generated by X? Well, certainly the subgroup generated by X should contain everything in X. Otherwise, it's stupid. You've got to contain everything in X. So what I want to do is I want to take all groups that are subgroups of G that contain X and intersect. So what I've effectively done is I've taken every subgroup of G that contains this set X as a set, and I intersect them. So in a certain sense, this is the smallest subgroup of G that still contains X. Right? By the way, notice that the subgroup generated by G is all of G, and I could take X to be the empty set. What's the subgroup generated by the empty set? Right, because I don't know much, but I know that every subgroup contains the empty set because every set contains the empty set, right? So effectively what you would be doing is intersecting all subgroups, but the identity is a subgroup, and that's clearly contained in everything else, right? So let me take you back to something. So here's a practical side. And you can prove these things are the same. The subgroup of X is a collection of all things in the form X1, epsilon 1, xk, epsilon k, where xi, x, and epsilon, or 0. So if I take that string of epsilons to all be 0, I'll call that the identity. So basically, here's the practical person's way of thinking about it. The subgroup generated by X is every word you can form from the letters that you might find in X, and their inverses as well. Right? So anyway, you can stick those together. Now, if there aren't any relations among these variables, this is what we call a free group. And we'll talk about this later. So there's no relations and there's no way to simplify anything unless you find something like X next to X, and you can call it squared, or X next to X inverse, you can call it the identity. But in more general groups, you might have relations, you might have ways to simplify this word and rearrange things in more simply, but if nothing else, you can write everything in this. Okay. So now that we've kind of cleared the way with that, so we know about intersections, and we've talked a little bit about making words and putting that together. Let's sort of do sort of the first mappy thing. And this is a short section, but it's yes, sir.
Is it, I guess, straightforward to show closure of, like, say, x1 to the k power that we're guaranteeing that, like, all powers of
Oh, sure, because if I want x, say x1 to the k power.
Oh, did these not have to be unique?
That's right.
Oh, okay.
Just do it k.
Okay, fine. Thank
you. Okay, so so I want to tell you, you all have all probably heard of cyclic group before. I'll give you a formal definition in a moment. But this is actually an important piece, and it's just nice to know from an art point of view. We understand what all cyclic groups look like, and also this comes up because, of course, every group has a cyclic subgroup, and so if you're wanting to try to understand a group via subgroups, which is a very natural thing to do, very common thing to do, it's nice that we have cyclic groups. We got that under wraps. We know what's going on. Just let me give you a reminder, what is a cyclic group? Over here, we were talking about generating a group with a set, right? Making all words out of this. Well, the simplest thing I can do is make the empty set, right? And then it's just the identity. The second simplest thing I can do is if this set X contains only one letter, right? Say little x. Well, what does a typical element of the group generated by X look like? Well, there's only X, right? And so everything's powers of X. This is what we call a cyclic. You could also say the identity is cyclic too. The identity is generated by the empty set, but of course you can also generate it with the identity itself. So there exists X and G such that G is generated by little x. And let me point out, I'm going to write the operation as multiplication. If you're generated by x, this is all power specs. Right? Because if x is in a group, then x squared, x cubed, x fourth, forever and ever have to be in there, as well as its inverses, right? So this subgroup generated by x consists of every single power of x, positive and negative. Now, notice I did not say those powers had to be distinct. For example, it might be the case that you have x, x squared, x cubed, and maybe the order of x is 4. X to the 4 is the identity, so you start over again. So that infinite list actually only contains 4 things. Let me give you a theorem, and we'll sketch the proof of this. We'll go through it quickly. And this theorem completely describes all systems. Theorem 2. Let G be a group, following conditions are equivalent. Number 1, G is cyclic. So there's one element in there that generates it. Number 2, G is the homomorphic image of Z. Let me point out that, of course, Z, the additive group Z is cyclic, right? It's generated by 1 because there were 1, 1 plus 1, 1 plus 1 plus 1, and the inverses are all negative. And Z is sort of the master, right? Because every, according to this anyway, every group that's cyclic is the homomorphic image of Z. 3. Homomorphic images of Z are cyclic. It's interesting that the homomorphic image goes in tandem with subgroups. This doesn't usually happen. All subgroups, I didn't even say the images. Say there. All subgroups. That's kind of interesting, right? Very rarely do you get this property. It's not generally true that if you have a property that its subgroups always have this property, but for cyclic, this is true. Isomorphic. C mod n. One greater than 0. Let me point out here. You might be making this connection already, but Z modulo, we'll get this when we talk about cosets, but Z sub 0 is 0, right? I mean, if you think about what happens to C mod n, you put things into equivalent classes, and you say 2 things are equivalent if their difference is divisible by n, right? Well, what does it take for 2 things to be in the same equivalence class mod 0? It means they have to be the same, right? Okay, so let me start the proof here. Three and 4 clearly imply 1. because all homomorphic images of G are cyclic. One homomorphic image of G is G itself, right? So this is that's kind of cheap. And certainly it's true that if all subgroups of G are cyclic, that includes G itself. And so there you go. So 3 and 4 imply 1. So the strategy we'll take is 1, 2, 3, 5, 4. And then by this, we have 1 plus 1 as well. Okay, so let's go to it. First, let's do 1 implies 2. Oh, I'm already saying 1 implies 2. So you have G as cyclic. You want to show that it's the homomorphic image of Z. Now, I am going to give you a homomorphism that's going to work for us. Z and should have been. Let's do that. Take whatever integer you happen to have in your input and take that to the exponent. Notice that V K1 plus K2 is K1 plus K2 X K1 X V and that's pretty clear, isn't it? Right? Because no matter what power I need here, there was an integer that corresponds to it. Notice this is subjective. I do not claim it's 1-to-1. In fact, it'll be 1-to-1 if and only if G is infinite. Usually this has got a big fat kernel. But that's all we need. Okay. Now let's do 2 implies 3. See, what we need here is G is the homomorphic image of Z. We need all homomorphic images of G are cyclic. Right. Well, suppose we have F and G H, and because remember what we're trying to prove here is all homomorphic images of G are cyclic. So this is an onto homomorphism. And what we have to do is prove that H is cyclic. So let's factor this map through here. So what we have here is G onto H. And I also know that G itself is cyclic. And so G is the homomorphic image of C. And this is by our assumption in number two, right? That G is a homomorphic entity. So we have this homomorphism that is done first by doing G, then F. Now, and it's on to. Because the composition of two onto maps is not the way of taking it. The last thing that I really need to do to convince you, I think, is to show that H is actually generated by. Right. I claim. By the way, what do you think the generator of H should be? Right. What you do is just, what's the generator of Z? Well, actually, you got two of them, but I'll take +1 is the additive generator of Z. Just follow this down the road. 1, let's see, we do G to it, that puts it in G, and we do F to it, generates it. Certainly, it's true that FG of 1 is contained in H. Because I mean, it's just that little image makes a subgroup of H. The only question is how do I know I get everything, right? How do I know that you have everything? Now that little H, G, and H. Now I don't know much, but I know the little H is actually F of some little G, F of some little Y, where Y is in G. Because this is onto. And what do I know as well? I know there exists, I don't know, some N in Z such that Y equals G of N. Because again, that map F is surjective. And so there must be some enter that goes to it, right? I'm running G and H multiply. So Y is F and G of 1 plus 1 plus 1 n times. Here I'm kind of assuming it's positive. I'm being a little bit sloppy. And it's positive, but it could be negative, and I could take negative 1. But at any rate, it doesn't matter whether it's positive or negative. This is G of 1 power, because G is a homomorphism. Right? So that's what Y is. Therefore, H is Fy, which is F of G of 1, N, which is F of G of 1. Which is an element of. So that's what we want. Everybody okay with this? Okay, so let's see. The next part of our strategy, I think, was 3 implies 5. We know all homomorphic images are cyclic. We need to show that G is isomorphic to Z n for some n greater than. This is like sort of revisiting what we did earlier. Notice that the assumption here is G itself is cyclic. so we want to show that G is isomorphic to Zn for some n greater than or equal to 0. So I'm going to break this up into 2 cases where G is infinite and where G is finite. So we're going to write G is a collection of N and Z. This is true for any cyclic group, generally a single element. If G is infinite, then P given by P of X equals N is an isomorphism. Let me give you a taste of this anyway. What's the first thing that perhaps we need to make sure of? I mean, I just kind of willy-nilly find this homomorphism. What might make you a little suspicious about it?
So XK, XJ.
Right. And let's worry first about well-defined. Well, is it? Suppose x to the n equals x to the n. Now, if this is possible where n and m are different, then I'm in trouble, right? Because it's not a well-defined map. Right? Okay, well, what can I do from here? Well, let's suppose, without loss of generality, we will say that n is greater than or equal to m. So we do that. So x to the n minus m is equal to the identity, correct? If n minus m is greater than 0, then G is 1x x to the n minus m. And that's a contradiction. Because suppose that n minus m is something like 5, right? Right, suppose n minus m is something like 5, then what happens is this will go 1x all the way up to x4, and then x5 is the identity, and you start over again. So the cyclic thing just lists these over and over again. And that means that there's only finitely many distinct elements, and that's a contradiction. Therefore, n equals m, and so p. And really, I'll let you finish this off. That's kind of the only thing, because now that you know it's well defined, the fact that it's a homomorphism and one-to-one and on-to follows from this. If, and there's one more thing to do, of course, and that is if the order of G is n, then let P go from G into Z n, given by P of K, oh, I'm sorry, P of X to K. And again, show well defined. It's actually very much like this, right? But once you have a 12-5, it's pretty easy to see that it is a surjective homomorphism. Okay, any questions? Okay, so the last one that we have, I guess, is 5 implies 4. G is isomorphic to Cn for some n greater than 0, then all subgroups of G are 6. Okay. So actually, this doesn't really matter so much because G is isomorphic to Cn, so G can be written right? Now I'm writing this multiplicatively, even though my notation in Cn, C mod n is additive. I'm writing this multiplicatively. Basically, you can, if you write it additively, you can forget about the n here. But if G is isomorphic to C, then these are just the powers of X as you run through the integers, and there's and all the powers are distinct, right? And if G is isomorphic to Cn, then you just repeat on the cycle like we did over here, right? But it doesn't matter, any cyclic group can be written this way. Now, let H so my claim is H is cyclic. Right? So so in particular, let me point out that H is a subset of Xn. So let's say now well, if H is the identity, I think we can all agree on the fact that the identity is cyclic, right? So I'll assume that H is not the identity. And among M in natural numbers, such that M and A okay. Notice the problem I avoided is the identity is really X to the 0, right? And so if you've got the identity subgroup, then there's no positive power of X at all in it. If H is not the identity subgroup, then it must contain some power. Do I agree with that? Now you might wring your hands a little bit and say, oh my goodness, what if it contains a negative power instead of positive? No worries, because it's a subgroup. So if it contains X to the minus n, it contains X to the n as well. So I'm guaranteed if it's not the identity subgroup to have some natural number such that X to the n is an H. And of course, any subset of the natural numbers has a smallest element. So we'll choose M to be smallest. So here we go again, crossing integers. I claim that H is generated by this particular power. G is generated by X to the 1 power. I claim that H is generated by this. Certainly, it must be the case. Certainly, you have that contained. The interesting part is the fact that all you need is power space. So to that end, now suppose H note that H X to the T. Because after all, H is an element of H, so it's an element of G. So it must be some power of X. Now I'm crossing my fingers and hoping I'm not screwing up at 8 more, and I hope that actually that T is divisible by M. Well, this sounds like a job for Brother Euclid. So let's take that T and divide by M, leaving some remainder R. All right. Like that. Now notice that X to the T, which is X Q M plus R, which is X to the Q M, X to the R is in H. X to T is in H by assumption. Both this, right? But notice this is in H as well, because X to the M is in H, right? And this is just the power of X to the M. So this animal is in H, and this is in H. Therefore, X to the T times X to the negative MQ equals X to the R is in H. But therefore, R equals 0, and so T equals M times 2, and so X to the T equals X to the M, which is in, and that passes on. So once again, fancy group stuff is saved by the simple Euclidean algorithm. Oh, by the way, just a quick plug. I am actually, did you grad students, did you get my math club announcement yet? Oh, okay, so it's actually passing through the moderators. It was your question the first day of class that inspired me to do this talk. I'm actually going to talk about Euclidean algorithm and how it relates to the fundamental theorem of arithmetic. So it might be fun for some of you. We'll look at some interesting examples as well. Okay, we need a couple of corollaries. 2.3. Okay, so one of the things that we take away from this, is that any cyclic group is a homomorphic image of Z. So as a corollary, any cyclic group in the analysis. So, I mean, the real numbers under addition, no freaking way is that ever cyclic. It's just too big, right? You can't have a single generator. Here's another corollary. If G is a finite of order n, and A and natural numbers is such that A divides n, then G has a unique subgroup of order A. I'm going to skip the proof of this. It's in the notes, but let me kind of give you a plug for it. Let me give you kind of a plug for this here. Let me point out that if you have then basically I have to write this way. Or I could write multiply that way. By 10, then n is a m. And so the order of the subgroup generated by x to the m is equal to a, right? Because it takes a iteration of x to the m to get you the identity, and there's no smaller one. So this actually generates a subgroup. The interesting part of the notes that you might see if you can sort through is the fact that this is unique, but it's not too bad. Okay. So a couple more minutes. So I'll kind of give you all sort of an introduction. Example. Y'all have seen cosets. How many of you are maybe a little hazy or yeah? So let me give you a couple subgroups. That itself is a subgroup. And let me do a couple of left cosets. When you look at this coset, it's actually a set. And it's what I just go through this and I multiply everything on the left by 1, 2. I can simplify this as 2, 3, and this goes 1 goes to 3, 3 goes to 2, and, yeah, that's 2, 3. 1 goes 3, 3 goes to 2, and 2 goes. Now notice if I put this on the other side, this is 2, 3, and this 1 goes 2. Notice this left coset, which consists of these 2 elements, has an overlap with the right coset, but they're not the same. When a subgroup has the property that it gives you the same set on both sides, this is a very important problem. But a coset is basically you just take a subgroup. That's sort of the soil that you plant it in, And the seeds that you put on the left or the right are just elements of the group. This creates a set. The cosets actually partition the group into a bunch of, well, the cosets are all disjoint. And this is actually going to solve this tunnel line. Well, let me give you one more group here that I call in for dramatic purposes. You might do a couple of computations like this, test your left cosets and your right cosets, and you will find that you get the same set. It may be scrambled out of order, but you will get the same set of elements every time. So we'll talk about cosets and that sort of thing starting next time. Any questions? Homework going all right for you guys? All right. All right, well, let me know if I can help you out. Other than that, I'll see you all by Friday. You guys got any questions out there?